introduce our session 15 speaker, Dr. Rahul Kala from Triple IT Allahabad. Before inviting him for his talk, I will just give a brief introduction about Dr. Rahul Kala. Dr. Rahul Kala is presently working as assistant professor and is associated with Robotics and Artificial Intelligence Laboratory, Indian Institute of Information Technology, Allahabad. Dr. Rahul did his BTech IT and integrated MTech from Indian Institute of Information Technology and Management, Gwalior. Then he did his PhD in cybernetics from School of Cybernetics, School of Systems Engineering, University of Reading, UK. He has authored 5 books. He has published nearly 100 papers in international journals, international conferences. He has also written 3 and the area of research, his area of research is mission planning for mobile robots, robot motion planning, intelligent vehicle and intelligent transportation systems, neural networks, evolutionary algorithms, hybrid soft computing, pattern recognition and classification. He is having an, 7 government funded projects of big amount. He has achieved several scholarships and awards during his career. So now I would request Dr. Rahul to unfold his presentation.
Okay, thank you for the wonderful introduction. It's a pleasure to be speaking at this wonderful FDP. So, my area of expertise particularly is into the autonomous mobile robots, AMRs to short. And I understand from the title of this interesting FDP that a lot of it would have been covered from the controls perspective. So I'll largely be talking about everywhere control domain where a lot of artificial intelligence meets robotics and the wonders that it really does therein. If you go to the market and buy a robot, which is the kind of robots that we deal with, this is exactly what comes. This one is Pioneer LX, of course, a discontinued model from Adept Robotics. After the takeover, they changed that over. It was taken over by Omron, so one of the leading companies into AMRs. And all it has is a differential wheel drive system, which gets around over here, same as what any one of you would do as projects with the Raspberry Pis and Arduinos. It has got in a front bumper, so if it collides, this is an expensive robot, approximately 25 lakhs at the time of purchase. So it saves it even if collision happens. There are ultrasonic sensors, the sonars which detect low height obstacle. For large height obstacle is a laser sensor, a system inside it, antennas for off-board compute. So in short, a standard autonomous mobile robots, that's a bit expensive because of this laser range scanner around over here. And what should we be able to do is do interesting algorithms with it. Now, what I'll not be speaking about is the fact where robotics was a couple of decades ago. So what people said, that is your robots, which by the way is a car from our sponsors, Mercedes-Benz, not in our campus. We cannot even afford it, nor will it work under our campus. it looks at some interesting things like vehicles, traffic sign boards, and it makes a decision based on that. So again, pretty much classic projects as I do call them now. So looking at it, you know that there's a U-turn coming up. If you want to go the other way around, you look out for that. You know that the white line is very close by, so you are more or less on the right-hand side. And you know that there are two vehicles. You need to be careful of that. Any deep learning library will give you all this information, and you can use it for, in AI, what we call as the rule-based decision making. Probably many of you are doing such kinds of projects where you'll annotate things around deep learning, can be done in real time if you have the correct GPUs, and make decisions for the robots and follow that up. However, I'll have an ambitious plan for this talk, and my ambitious plan is, can a mobile robot like this, my office, a mobile robot like that do whatever I want it to do, which is travel around this beautiful campus? And if it has to do that, what are the problems that it will have to solve? So these are the problems as we know. Vision is as stated in the last slide. So understanding whatever things are around. I'll primarily, for the first half, be speaking about these two interesting problems. Localization, that says, where am I in this world? So what are my coordinates? What's my orientation? With respect to the map, what is my position? And that's called as the problem of localization. Mapping is, what does the world around me look like? And the two problems are pretty interesting. Even if I ask you right now that a doorbell rung while I was giving this talk, you need to go and answer the doorbell. So you can do it pretty interestingly, but if you had a robot, how would we be able to go to the main door? It should know where the main door is. It should know how the rooms are connected to each other. It should know in which room is the robot at. And therefore, same example, if I just uplift up a little bit, if it was the famous Allahabad Museum, I have to usually ask people, how do I go to the entrance where somebody is waiting for me? Because usually I don't have a map, and because I don't have a map, I don't know how to go. Sometimes it's more interesting. The museums give me a map, which is a nice detailed representation of where am I? I'm still not able to go because I don't know where am I in the map. So I'll have to go to a guard and say, can you please point me out? Where am I in this map? Because I've got lost. So unless you know the map and unless you know the location in your map, you cannot do navigation. That's the central point of my presentation. Now then, of course, it turns out my other half of the talk would be that given that you know where you are and what's the map, how do you construct a trajectory that goes from your current location to your doorstep, which is your goal? And of course, I won't be talking about it. Usually there are a lot of people who talk about this problem of control. So given a trajectory, how do you really control your left and right motor? So I'll go exactly in the same order: localization, mapping, and planning. That's my index of the presentation. I won't be talking about vision believed to be known with all the object recognition and all the wonderful OpenCV libraries. And I won't be talking about controls. It's classic problems. I believe most of you would know it. So the first question is that I need to answer is where the robot is. And in order to answer where the robot is, in AI, every decision is made based on the eyes. So the question will be answered based on sensors. There are two types of sensors touch. The first one is called as a 3D LiDAR. So all it has is a laser pointer similar to the one that I am using for this presentation, except for the laser pointer sends the beam that strikes the object and comes back. So I know the distance to the object, and this laser beam can turn 360 degrees. So I get what is called as a depth image. You would have seen this depth images in movies, typically by radar, where they try to show how do they detect in foreign planes. And of course, there are multiple such beams at some angle. So I get multiple depth images to give me the height. This is a standard stereo camera, a left and a right camera that's used to compute depth because of the same principle. Two eyes can compute depth. So my first problem is, how do I know my location? And the answer is pretty intuitive. This is what you see as a 30 km/h signboard taken from an actual highway at Bangalore, thanks to sponsors for the data set. Now I say, if I tell you what is the exact coordinates of all these corners that make the 30 km/h signboard, intuitively saying that from the nearest intersection, which is taken at the origin, this is at 25 meters, and my vehicle is 4 meters behind this signboard. So I know that my position is approximately 25 minus 3, which is 22 kilometers from the last signboard, from the last intersection. So given all these coordinates of all the signboards called as landmarks, signboard is too specific. Let me generalize as a landmark. So given all these positions, I can calculate my own pose. If you want to be a little bit more formal, I say the pose matrix of this signboard is known. The pose of this signboard matrix is nothing but the pose of the vehicle times the pose of this signboard in the vehicle coordinate axis or the camera coordinate axis system. So I know two of the three matrices. I can calculate the third. If somebody knows transformations, otherwise, it's just the intuition. So that's one way I can calculate my own position. My input is the pose of whatever I am looking at, and my output is the pose of the camera, intuitive. You may say that, how do I know the pose of this 30 km/h signboard? That's a bad assumption. So the other way you can look at it is, look at these two images, and you see that the signboard was earlier at 5 meters from my camera. It's now at 3 meters from my camera. The signboard did not move. So what moved? I moved for 2 meters, and just looking and tracking at the signboard, I can calculate my own pose. So when I look at it first, I say it's position is my pose times where am I looking at with respect to myself. I do that calculation and I register it at, say, 25 kilometers from the origin. Now I'm looking at it from a certain distance. So here it was 5 kilometers, here it was 3 kilometers. So I would have moved 2 kilometers, and that's what I say is my position. I assume my position at origin is known perfectly. Every time I keep a track of signboards like this, how much have they moved? They haven't moved, you have moved. A funny thing, that is also how you try to guess the speed of a train, whether it's moving fast or slow. You look at the signposts outside the window. If the signposts move very fast, the speed is high. If the signpole moves slow, the speed is low. The signposts never move, you move. Same technology. And of course, the latter one has a problem that suppose you make an error of 100 centimeter in this frame, then what happens is after this signboard goes back away, you're using this one up, is 10 centimeter error already made plus the error in tracking this signboard. So your errors keep on increasing with time. And depending upon your sensors, sometimes for outdoor after a couple of kilometers, sometimes less than a kilometer. For indoor, sometimes after a kilometer run, sometimes after a few meters run, the thing is not reliable at all. Now, it turns out that for the indoor mobile robots, we also have what is the motion encoders. And you people know that I can measure how much the wheel has turned. There are spikes on the wheels, and there's a transmitter receiver. So I get pulses, and I can count the number of pulses. The problem is when the robot skids and slips, there is translation, there is no rotation. So again, the errors keep on adding up. That's why the robots that we purchase are so expensive. The wheels are anti-skid and anti-slip. So again, another way to get the location would be using a IMU sensor like the one in the mobile phone. It has an accelerometer. Double acceleration of accelerometer is a position. Bad idea because the accelerometer reading is true reading plus noise. A double integral of the sensor signal also double integrates noise, and that's a lot of noise. So be it wheel encoders, be it accelerometer, or be it vision-based tracking like this, I integrate noises and therefore my errors keep increasing. On the other hand, if I say that the pose of every 30 kilometer per hour signboard is known, it's absolute, I get perfect positions. But the assumption is, how do you get the 30 kilometer per hour signboard? I'll not take the other idea of integrating noises. I will go with this idea that somehow I need the pose of all the 30 kilometer per hour signboards. I'm not interested in integrating errors. And therefore comes the problem of mapping. Or how do I get all the 30 kilometer per hour signboards which are here? Not all of them are 30 kilometer per hour signboards. Some of them are U-turn, some of them are the diversions, and so on and so forth. So how did we do this one? We took the vehicle on a spin like this. into a street, into a highway at Bangalore, and by some magic, we always knew the position of the vehicle. So if I would have shown it in real time, you would have seen, like Google Map, the red dot or the vehicle moving like this. And then what do we do? The moment I see a traffic sign board, I say, I know my position. I know the position of a traffic sign board with respect to me. A weird mathematics called as transformation. I know the traffic sign board sign with respect to the world, and I just put a red dot. I see the same red dot 10 times. I take the average of them, and that's how you get this map. And that's accurate, that's known. The only problem is, in this mapping, the position of the vehicle is the input and the map is the output. The position of the vehicle is the input and the location of all these signboards is the output. Or the map is input, my location is the output, and you see that the two problems are interconnected like chicken and egg problem. If you have the map, 30 km/h signboard locations, you get your location. That's the problem of localization. If you have the location, your own position, you get the position of all the 30 km/h signboard. So position gives you map, map gives you position, neither position is known, nor map is known, and that is what we call as the problem of simultaneous localization and mapping. This one was using a stereo camera, just the left image shown. This one is using the other sensor LiDAR. So the second laser resolution, so they are multiple on top of each other. This was taken outside my office, and this is exactly where I am. You see a narrow entrance around over here. That's just a lobby that we have because this is the entrance of the head of robotics, and that's the lobby that goes around. So here, of course, there is no 30 km/h signboard. However, I can track corners like this. How much do these corners move? And my position is how much these corners move. I can keep on integrating that. So before I really touch upon, how do we solve the chicken and egg problem, that's just a simulation for outdoor scenario. The black dots are my landmarks, previously called as 30 km/h signboards. Now you can see they are corners of all these trees and corners of all these light posts and corners of everything that you see. Those are my landmarks. Every corner can be tracked. So all corners are your landmarks. And this is a beautiful campus. And you'll see that I am simultaneously localizing, shown in blue, and mapping, shown in black. The black landmarks increase with time, and based on which I calculate my position. Once I know my position, I register more black marks. So position is given map, map is giving position simultaneously. For the ones who like it more visual, this one is indoor. This is the laboratory. That's the robot. That's the Kinect sensor. And you can see the map is being made. The blue ones are the pose. So the blue ones are giving the map and the map are giving the position. The features are not shown. The complete map is shown. And that's a beautiful one. So this is the entire campus from which I am making this presentation, I am somewhere around over here presenting this one. So very quickly, how do I really solve the problem? Now we know there are no 30 km/h signboard. Every corner is a signboard. So I extract all corner using any technique. Sift and left and a right image. So I extract and match the left and the right image features. And if I know my position, I can triangulate and register it as a black dot that you saw. However, if I don't have my position, I will calculate that. So any one of these dots is represented as a cartoon like a red dot. And the pose not shown in this figure where the camera is placed is shown like this blue circle, and the cartoon says that how do I calculate my pose given the XYZ of all these points, given the XYZ of all of them, I need to calculate my own pose. I hate equations, so I did not say that. I only want to develop the intuition. Every edge is this feature with this XYZ location is observed at a specific UV position, and because it's observed at a specific UV position, I say if I did not have observed it up, what should have been the position of this feature given a pose of the camera? Again, there's a mathematics behind it that says the UV value is the calibration matrix times the pose of the robot times the pose of the feature. How I'm not teaching you transformations. So I have made an observation. So I try to optimize for my pose as much as possible so that where did I actually look at the feature and where the feature projection by mathematics happens should exactly be at the same place. So depending upon your city, you say that you saw the famous Chauraha of your city, and then you say that, okay, that is what I know. The Chauraha's XYZ is known accuracy. My is telling me I am at this coordinate. If I am at this coordinate, this Chauraha's coordinates are known. So inside my brain, the Chauraha should have this as the UV value in the image that my brain takes. In reality, I'm looking at the Chauraha and I know where am I looking at. So that is the actual UV value. The two do not match. So my wife is wrong. Of course, I will correct my wife's suggested pose so that where am I looking at and my back projection where I should look at are exactly the same thing. That's how you calculate the pose. Now let me do it the other way around as well in the same cartoon. So suppose you know the pose and you do not know the XYZ of these red marks. You don't know that. Earlier I taught you this cartoon as a localization problem. Now this cartoon as a mapping problem. So you saw some corners around here whose XYZ is not known. You know your pose. You know the observations from left and right camera. So you know where is this point in the camera frame. So the XYZ of these features is the pose matrix of the robot times the triangulation done in the left and the right camera that gives you the features. Mathematics, not important, you will get it at any book. I usually don't keep a lot of mathematics because then I start to sleep and then the organizers have to come and wake me up. I better not sleep in this one. There's no one to wake me up, so no mathematics around over here. Let's have this cartoon. So, I mean, it's still chicken and egg problem. So let's very quickly solve the chicken and egg problem. I say that there is a keyframe. So using this keyframe, I solve the mapping problem. I get the XYZ for all these points. Suppose this keyframe, the position was known, and then I back project them and get my own pose. So the keyframe registers these red marks, and the pose is using these red marks for localization. Why do I say I have solved that up? Because the first keyframe will be at the origin. After some time, what I'll do is the first keyframe is at the origin. I make some movements. The second keyframe uses the registered point to localize position is known. Then it registers these 2 points. This keyframe uses these 2 points to calculate its location. So I continuously, that's exactly what I said. I keep on registering keyframe, back projection to compute the position. Using that, I compute new red marks points. That's called as SLAM. And in pursuit of which, what I have unfortunately done is that I'm still integrating errors. I know this origin very well. There's 10 centimeter error to register these 2. So this position is calculated based on 10 centimeter error. So there is a 10 centimeter error here, and the optimization is not perfect. So there's another 10 centimeter error that becomes 20 centimeter. So this is registered with a 20 centimeter error here plus another 10 centimeter in looking at it. So the errors accumulate, and the only way to stop the errors from accumulating is start from a point. This is where you say is the start of the Chauraha that you were trying to calculate your position, where is an iconic signboard, and that signboard says this is the start point. You keep on rotating around the Chauraha, you are either confused, you don't know where to go, or some other reason. That's how you go on a morning walk. So you're losing a lot of weight as I move the laser pointer. And then your slam technique says that you are here, but you observe the same signboard which you started off with. Now the signboard cannot change. It means you accumulated this error. When I started my morning walk at the Chauraha, I saw the signboard established 1829 by the biggest personality of the time. And with that inspiration, I started the morning walk. I had only reached here, I saw exactly the same board at exactly the same position. Now, that means I'm not here, I'm actually here, and this is the error accumulated. So what I do is I go back with time and I correct my positions with this knowledge. So I virtually stretch and pull this over here, and I correct my past. When I correct my past errors, and because when I was making this work, I saw many things and I registered them in my mind as all those black dots that you showed. So I go back and I correct the position of those black dots. That's how you stop drift from accumulation. Now, I'll be talking about the second part, which is what I like to speak more upon, is the motion planning problem. So this is again the map of my own place. This is where I am taking this webinar as. Now you know when I said the corridor in the depth image, this is the one that I was referring to. And this was the open area that you saw in this depth image, this one. So this is the open area and this is the corridor. So to match it in this map, this is the open corridor and this is the small lobby area that I said. Now you see, I mean, the moment you place the LiDAR image on top of it and get everything, get these corners. So there I referred them as a corner and I said that you can actually, if given a map, calculate your own position. I just proved it how. So place the two corners here and you can calculate your own position given this map. So this is the map over which I'll be working, and all I want is the robot to go all the way up from here to here to here to here, all the way up to here. That's my problem. I am so lazy that I ask a robot to come and do petty jobs for me. Once upon a time, I could have asked my PhD students for that. Now they start complaining, we are not meant for that. They're meant for PhD, they don't even do that. I still love them. So the PhD errors are all. So that's a trajectory that I eventually want to construct so that my robot can do the petty jobs that I have. Just a brief of how do I make this map, of course using SLAM. This one is a little simpler because my wheel encoders are highly accurate, and unlike last time, a laser costs significantly a larger amount of money as compared to an image, which is a stereo camera, so it's more accurate. So mapping, what you do is you keep on taking the images that I just showed you and you keep on stitching them up, matching corner to corner, so you get a complete map. It's been pre-processed a little bit to straighten out lines like these. And for the location, you find out the corners and then you match corner by corner to find out how much the robot has moved. So same technique, you get your location, same technique, you get your map, and same technique, just like I said, you look at the established 1825 sideboard and then you say loop closure has happened. You start from here, you go from here, the depth image exactly match. That's when you say that the loop closure has happened and you make certain corrections. Indoor is a lot easier. Map is under your control. The lasers are more expensive. Last time there were too many moving vehicles. This time, strictly by order. When it's mapping, nobody is allowed to move. Even I have to move behind the robot, so everything is controlled. Now what we'll do is, we will make a technique that can generate this trajectory for me, and intuitively, even if most of you may not have a computing background, the most basic algorithm to compute anything like this is called as a graph search. And a graph search algorithm is place grids like this, divide grids, and connect every grid with its neighbors. So this will be a small grid. This will be connected to all the neighboring grids. And once you do that, you have a graph. Once you have a graph, you can use any of the graph search algorithms possible. So that's up to you which graph search algorithm you use. Wonderful technique. Now, there are two problems around over here. The first one, the robot has a size, and the robot is circular. But then there's a famous theorem that says if your robot is circular with a radius r, all you do is you make the robot as point size and you increase the size of the obstacle. That means these obstacles get inflated by the radius of the robot. Now there's a second problem, that this region is extremely thin. If your grid size is larger than this region, then it can never find out there's a free life. There was a time when we used to click photographs and then we had to decide at what resolution to store it up. So if you store it at a high resolution, you need a lot of hard disk space. We were poor students back then. We did not have that. If you store it at a lower resolution, you would be like 20 years down the line, this is the photograph that I'm going to cherish, and I'll hate a low resolution. So it was a very difficult question. Same with videos. At what resolution do you save them in your hard disk? Even now, it's a very hard question. At which resolution do you watch this video? If you have set too high resolution settings, you or your university like mine are very expensive. So, I mean, they are very rich. So you have a lot of bandwidth. Our students face this problem. At what resolution do I look at the lecture? I've got 2 GB of data and I have to manage everything up. So high resolution is better, but then you've got the budget. Same thing with mobile robots. My time is limited. I don't want that the robot should work at a very high resolution and get this trajectory in 10 seconds, and I'm waiting for 10 seconds looking at the screen. Why is the robot not moving? It's more important because the search happens at a space whose dimensionality is equal to the dimensionality of the robot. So for a 6 degree of freedom robotic arm, it is a 6-dimensional space. And in 6-dimensional, resolution is very important because exponential complexity. 2-dimensional is still okay. For a drone that takes surveys, the dimensionality is again 6. Today we have humanoids with up to 48 degrees of freedom. So it's a very high dimensional space, and I cannot do a grid search. In AI, whenever the exact algorithms will fail, the approximation ones will come out. So this is the approximation algorithm of the same graph search. And in this algorithm, all that I do is that instead of dividing it into grids, X and Y, I take random points. So you see the vertices are completely random. And every vertex, I draw a circle of radius R and connect them to the neighbors. And these are the blue lines that you see. Now, if I repeat this for all the vertices, you'll get a connected graph like this. The only problem is that even this is computationally expensive. I don't want my robot to really wait for that long. And therefore, what do I do is I say this map will be made offline. When I say that this map will be made offline, all that I say is that whenever we get a new robot into our laboratory, step number 1, we unpack it up. Step number 2, we take lots of photographs and update all our social media accounts so as to tell the other peoples, yo man, we're doing high-tech research, and there's a long queue outside the robots. Everybody wants to update their profile pictures and tell their friends that they do an awesome job. They just opened a box. Step number 3 is you make a map like this. Step number 4 is you make a roadmap like this. As simple as possible. So it only depends upon the static obstacles and the robots. Both of them are known. So you do it immediately. And because you do it immediately, you save it at the robot map itself. That's called as a roadmap. The problem of doing that is that I want to go from here where there are no vertices to here where there are no vertices. So how do I go? The source and the goal that I want to go and construct a trajectory is not even a part of the roadmap. And therefore, what do I do is that I temporarily add source and goals, which are shown by this dark green. They are temporary. I'll remove them up. If I don't remove them up, my map will grow along with time. So 100 queries a day, 365 days a year, every query adds 2 points, source and a goal. Then the number of vertices become too large. My map cannot be growing with time. So I temporarily add a source, I temporarily add a goal, I connect it up. Now you can use any graph search algorithm. So it's up to you which graph search algorithm you use. It's entirely up to you. You can use any graph search algorithm and get this part. Suppose you do not get the part. it could mean two things. One, it's not connected. Secondly, the number of vertices and edges are not large enough. If the number of vertices and edges are not large enough, then you can always add more vertices. So like last time, there is still a resolution factor, which earlier was the resolution of the grid and now is the number of vertices and edges. But unlike last time, if you decide to increase the resolution, you have to do everything from scratch. Now it's simple. You don't need to do everything from scratch. You just add more vertices and do a new search. Your old vertices and your old roadmap is intact. So you keep on adding vertices and edges until you get a path like this. That is what is the probabilistic roadmap technique. And this one is for the map that I showed you. So this is the graph search, what it'll get you. So that's into my office. That's a graph search, and that's a roadmap. Now I'll speak for just 5 minutes about a formalism that I usually skip. But then I said that, okay, let's try to get this formalism this time and see what happens. So the next couple of slides, even if you get nothing, you are the most normal person. None of my students have understood it, but I'll still make an attempt. So in AI, what happens that whenever you get a robot, you first find out what are the degrees of freedom of that robot. So in turn, anything which can move is 1 degree of freedom. So you've got this kind of a robot over here, rectangular. It can move in X and Y. So degrees of freedom is 2, which is in X and Y. So we construct a new space called as configuration space, and every degree of freedom is a new axis in this high dimensional space. Now, value is black if the robot at that particular point collides. So what you do is, I want to find out whether this is black or white. It has all the degrees of freedom as an axis. So the position that it can take, its complete encoding is a point. And because it's a point, you close your eyes and you visualize. I office and people mistake it that I am sleeping, and then there is a nice chaos. Researchers have terrible times when closing their eyes. So with nobody looking, you close your eyes and you visualize a robot exactly at this X, exactly at this Y in the space. It's a ghost robot. So don't take a physical robot and place it at that X and Y. If that ghost robot collides, you put it as black. If that ghost robot does not collide, you put it at white. A cheat over here is that you place a ghost robot in this physical environment such that it just kisses the obstacle boundary. Not the best love story that I would have thought of. If you move it a little bit inside, it'll collide. So basically this obstacle will be nothing but this obstacle and increased by the size of the robot. That's exactly what I said. Circular robots, you can just increase it by the radius. Rectangular, you can just increase it by the length and the breadth, and you get the configuration space like this. That's the boundaries increased. It gets a little bit more difficult. So I mean, if the boundary is small enough, the robot cannot fit in. You increase this, you'll get exactly the same thing. It's a fat robot. During lockdown, it gained a lot of weight, and now earlier in childhood, it could have easily gone here. Now it's fat, it cannot fit in here. What a poor guy. Either will have to reduce weight or will have to take the longer way out. And guess what? Taking longer way out multiple times will get thin enough and will be able to use it. Robots don't get thin, they retain their size. Okay, so very quick example, if the robot could have gone in X, Y, and also rotated, so there are 3 degrees of freedom. This robot can travel X, travel Y, as well as rotate. The rotation is shown by this arrow. So it rotates 90 degrees, so the arrow instead of right becomes up. So my new space, configuration space, will have a x-axis, y-axis, and a theta-axis rotation. I'll do exactly the same thing, and then I will put this black and white image as you see it. Um, that's for the manipulator. So the encoding is two angles. So it's an arm. So that's the first arm. That's the second arm. The first arm has a degree of freedom. The second arm has a degree of freedom. So that's the first degree of freedom. That's the second degree of freedom. And I do the same experiment. If the arm is hitting an obstacle, it'll actually overlap an obstacle. You don't do it with the physical robot, with a ghost robot. Then I put it black. Otherwise, I put it white. The funny thing is the obstacle looks nothing like the actual obstacle. So obviously that's the funny thing. So this obstacle is this one and this obstacle is this one. It's circular. So you see the actual obstacle is like this because I cut the axis 0 to 2 pi is equal to 0. So this thing which was here went up here and similarly here. It's also circular on the theta 2 axis, but then unfortunately there is no obstacle that you can visualize it up. And my last caveat before I get you back and wake you up, the impossibles are gone and the fun will continue. So constructing this image is for 48-dimensional robot is infeasible even by modern computing. So you don't actually construct this entire space. What you do is you put in random vertices all around. Then you see, is this sample black or white? If it's black, you don't put it. If it's white, you put it. So the probabilistic roadmap really does not construct this entire image. It just checks whether these points are black and white. And if these are white, then you admit it. If it's black, you don't. And it checks for this edge. Now checking if and this edge is black or white, whether this point is black or white, and whether this edge intersects an obstacle in its traversal or not, is a problem of collision detection. And there are famous libraries that use geometry to find that out. So you just call a straight library of collision detection. A lot of people try to enter into collision detection. It's a domain of mathematics. So if you take a deep interest in geometry, it's a wonderful thing to do, but it's pure geometry to find out whether a robot kept at this encoding, which is a geometrical figure with all the planes defined, and the environment which has tables and chairs and everything detected with all the planes defined and the beautiful surfaces defined to find out whether two surfaces intersect or not. It's a purely geometrical problem, and it's a beautiful geometrical problem. The only thing that in IT we do in addition is that we store the map in a hierarchical tree-like manner for computational reasons. So you don't have to check for all combination of surfaces. You have to check for the nearby surfaces, whether those nearby surfaces collide or not. So very quickly coming to a problem that I did not tell you. So people at Stanford and all these pioneers of AI wanted to solve robotics problem for 2D robots, circular. They solved it very easily. Breakthrough came with the A-star algorithm, which is, of course, a grid search. Then there was a problem. Somebody developed a planning problem for a manipulator, 6 degrees of freedom, drones, 6 degrees of freedom, and the grid searches weren't scalable for 6 degrees of freedom. And then came in the probabilistic roadmap, could easily solve that up. But then, of course, the problem came in with extremely complicated environments. So a classic problem, which is the one that I enjoyed the most during my days at the lockdown when our domestic help did not come and we were in an extremely bad shape. So it's robots in kitchen, and our kitchen is the most weird kitchen. There are boxes behind boxes, there are boxes aside boxes, and then you actually have to take your arm and then get all the equipment out. I have no idea why in Indian cooking you need all the ingredients at one place. My days in the UK were better. Get something pre-cooked, put it in the microwave, done, not in India. So when you have such complicated spaces, imagine a 3 degree of freedom mobile robot, on top of it a 6 degree of freedom arm, 9 degree of freedom operating in your house. Now there are too many integrate things, and two things happen. One, there is no static map. Your kitchen map depends upon who last cooked, would have displaced stuff and items. There's no static map. So PR probabilistic roadmap cannot work, static map. The second is some places are more important. In order to decide in how to put the salt inside your dish, why would you consider things which are very far off, like clothes hanging at the balcony? That's a separate problem. It's in a separate space. So probabilistic roadmap looks at the complete space. I need something which is more focused from the source to the goal. Something more focused from the source to the goal. And if I know the source and I construct a live roadmap, it has to be a tree. It cannot be a graph, because graph will have a cycle. And if the source is known, the graph just tries to predict the shortest path from source to everything. A cycle can be broken into a tree. One edge is what will never participate. That's geometry, by the way. I'm not telling you the difference between graph and tree. That's for people in algorithmics. Now, of course, that's an easier idea. So what I do is I plant something at the source, and it keeps on going in all directions. The moment it hits the goal, it stops. So this is me standing at the kitchen with my arms down, and my arms are moving all around. Ghost robot, believe me, not the physical robot. If a robot keeps on doing all these actions, it will eventually collide and break and won't be able to do any other action. This is all the actions being performed by a ghost robot, and whichever sequence of actions reaches to the goal, then you say, hey, the path is found. And what I'll do is I'll make this tree more directed towards the goal. So you see that a lot of expansion happens towards the goal, very little happens away from the goal. And that's what is the latest in robotics. So if you get a state-of-the-art robot, if it's only a mobile robot which which is circular, it doesn't matter what the planning algorithm is. It's too simple. If you get a manipulator, this is the typical choice of algorithm used. It's the rapidly exploring random trees. It's rapid, so it just keeps going in every direction. It's random, it grows randomly, and of course it's tree. This one is biased a little bit towards the goal. So that's more or less the standard right now. If you are talking about a mobile robot, now there are reasons to believe that even RRT is a standard out over there. But then it turns out that there are ways to solve the resolution problem that I did not do. So many of the classic robots, they still use a multi-resolution graph search. So as an only increase the resolution where there is a confusion, which is around narrow corridors, rest let it be. And quickly coming up that the standard library is called as the Open Motion Planning Library. The visuals are from this library itself. It's customizable. It's open source. Install it on a Linux. It has a lot of tutorials and help available. This one is a recent library in contrast to the others that many people would have told you. So if you want to get published really fast, like sometimes what I do with my students, it's open source, you just change a few codes, it makes all the analysis and it does all the analysis and makes all the graphs itself, and then you can just copy paste the output of this library and write wonderful papers. That's the Open Motion Planning Library. It's used to be primarily sampling based, which is the probabilistic roadmap and the RRT that I taught you. And now it has other planners as well, just because it's become the state of the art and people are saying, but my planning problem is very simple. So optimization is a better technique for me than PRM and RRT. So these people said, yes, we will do that as well. And of course, as we speak, because it's open source, all the schools of learning are trying to have their solution in this framework. So I do encourage, if you are into motion planning and robotics, just have a look at this library, just see, play around and see if you like the visuals over there. The last segment of my ambitious talk, I've never tried to cover so much in a single talk. Usually these are 3 separate talks or sometimes 4. So the last segment of my ambitious talk will be on one problem that hasn't been solved yet. So we started off with 2 examples. I mean, number one, the robot has to come to my office. It does all this PRM RRT thing. Wonderful, it's a simple problem. The second one was more to do with manipulators. Now, taking the first one as a specific example, there's a problem, and my office usually has a lot of people. So I'm the bad guy at IIIT Allahabad. I make the lives of a lot of people a hell. I love them. I still do that. So everybody is coming to my office, giving me dhamki. It's Allahabad, UP, and giving ransoms for me and stuff like that. And of course, after that, they do go to let the other guy do exactly the same thing. So my office is a very active place. And a lot of people are coming and going. And what happens is the map is continuously changing by people moving. So by the time you plan for RRT and the robot can execute that plan, the map changes. So another guy is outside my office who is pacing. And the moment the robot makes a step, this guy moves even further. So that's what's reactive planning. A simple solution to it. There is an absolutely simple solution to reactive planning. So that's your robot, and it is having a high negative charge all around it, and the goal is positively charged. So what will happen, the positive and the negative will attract each other, and the robot will go fall in love with me and try to come as much as possible towards me. So that's what I like to do. I like robots visiting me. With time, I have developed weird interests in life. Now it's robots. That's what happens in engineering school. So the robot loves me and comes over here. Positive and negative charges attract, but all these obstacles have negative charges all around them. So the robot also feels repulsion. So this robot will feel repulsion due to 3, which is this obstacle right here, repulsion due to 1, which is this obstacle right here, repulsion due to boundary here, repulsion due to this obstacle, which is here. Okay, this is too far by. Inverse square law, something too far off does not even have an appreciable attraction. Like, because of the law of gravity, wherever you are, we both have an attraction to each other, but you are so far off that the value is negligible, it's 0, and that's attraction towards the goal, and that's how the robot obviously goes around and reaches the goal in a real quick manner. That's a cartoon that describes the same concept. So you say that what you do is everything will now have a potential. So the goal attracts everything towards itself. So goal is like the Sangam of Allahabad. So everything eventually goes into the Sangam. So it's at a slope and everything will go at the Sangam. So goal always attracts. Anything, wherever you are, you will go and take a dip at the Sangam. So that's your goal. The obstacles, they repel each other. So you cannot be on the obstacle and they all repel each other. So the obstacles continue to repel you up. And because you continue to repel you up, if I add total both of them up and I slice them around over here, that's a beautiful picture. So anything will eventually take a dip at the Sangam. If it comes over here, what it'll do is it'll have a nice route and eventually go into the Sangam. So that's your robot. It'll eventually go around over here. Now there's a problem, and the problem is pretty profound. And the pretty profound problem is that all this nature-inspired things have a major problem, and that's called as a local optima. So, I mean, fun story that yes, I do attract a lot of people because of my charm, and they do come mad after me, but then there are some villains who will just form a obstacle around and they won't let me come. A lot of people here, especially at our campus, they love their counterpart, girlfriends and boyfriends. They want to go, but the lockdown is what is the barrier which is not letting them meet. And that's exactly the same thing that happens around over here. So if I very quickly draw this up, so this is whom I love, that's the robot, that is me. The robot wants to come, attraction, repulsion, everything, but then it cannot because that's a barrier. The actual way is, of course, to go around like this. And that's what we say, that the robot is stuck at a local minima, which is this, and it cannot come at the global minima, which is this. And always you see the robots get stuck like this. And that's in fact the very first experiment that we did. The robot was actually closer to where I showed you, and my office was here. I was waiting for a brand new robot. I was like, it's coming, it's coming, it's coming. It never came because it was trying to break the wall. And something going on in the presidential elections anyhow. So the robot was trying to break the wall and come all the way around over here. Of course it couldn't. It would have broken itself. So it got stuck at the local optima. So the unfortunate thing, a student actually had to carry it all the way here, and then it came running for me, and I was so happy. Then it could even avoid a few people around. I was still happy. So that's one of the problems that I'll try to solve. Now, the literature has a very obvious solution to that problem. Okay, I'll talk about that problem later. There's a second problem I should have introduced first. What happens in an algorithm when they are moving people around? So let's take a shy at the old algorithm. So that's where the robot was originally. This is my goal, and this is the trajectory planned by a probabilistic roadmap, RRT, whichever algorithm you like. So that's a deliberative trajectory planned by any one of these. Now, just because there is a goon outside my office, I have no idea how it did it clear a national level security that we have outside. Sometimes they even stop me from getting inside. So that's that's just a goon which is, hanging around my office, and that's how the goon is going. And eventually what happens is that my plan will of course get deformed because there's a moving obstacle that hasn't been accounted for. Now, biologically inspired, there's something called as a rubber band. The rubber band is the same equipment how sometimes my wife keeps all her hairs nicely intact, and I never know what's the actual shape. So the beautiful thing about a rubber band is you can make it go any shape. So you tell a shape and the rubber band will form that. You just need enough fingers to hold it at characteristic points. So people love the rubber band, also called as an elastic strip. The other beautiful thing is you let go of the fingers, it comes into a straight line. So that's exactly what you say. This trajectory computed by RRT PRM is nothing but a rubber band. And now you need something which will keep it away from being deformed. These are these obstacles. These obstacles exert a force on this rubber band. No, go away, go away, go away, go away. And because they exert a force, the rubber band cannot take its natural shape. So as this goon comes in, it's forcing the rubber band behind. What's happening is my trajectory is always in shape. It's always collision free. The other way to look at it is do it the other way around. As this obstacle gets away from here to here to here to here, the rubber band comes back in shape. So the trajectory is always locally optimal. It's always collision free. It's supposedly something that can solve everything. The whole problem is that if this obstacle moves extremely fast, and if this keeps on going like this rubber band will break. And if your rubber band breaks, you can buy a new one. You can construct a new trajectory, but then the robot will have to wait and construct a new trajectory. It's not real time. The searches are not real time, so it'll have to wait and construct a new one. Sometimes you actually go with multiple trajectories. So the moment your rubber band breaks, you say, okay, I have a plan B, and you continue going out with your plan B, and that solves everything up. Now it so turns out that I showed you example or that the elastic strip, which is the probabilistic roadmap technique, or the RRT technique giving you this trajectory, can avoid one obstacle, provided it doesn't break the rubber band. If it does, then the backup is always there, called as the elastic roadmap. So, however, it cannot handle too many moving obstacles, and especially when the session is going around over here, my office is a complete chaos. There are students trying to convince me to increase the marks, and they storm around in big numbers. So for so many people, I cannot maintain my rubber band. I cannot maintain my elastic strip. So that's too many people to compute. But if I have to move out, it's very simple. So just keep finding the gaps and just keep going through the gaps and go out. So it's obviously a very simple algorithm. So coming to the same problem again, that probabilistic roadmap, and so coming to the same problem which is here. So the probabilistic roadmap is a very good technique. The problem is it cannot handle dynamic obstacle. The potential field is a very good technique. The problem is it gets stuck in a local optima. So how do I solve it? The probabilistic roadmap technique, or the RRT technique. Okay, now let me be as generic as possible. So the first one is called as a deliberative algorithm. A deliberative algorithm is the one where you think a lot. Like as an academician, I think a lot on what questions to put in the question paper. I waste a lot of time. That's deliberative. So you find out the best combination possible. You think a lot and you find out the best trajectory possible. The problem is that it works only for static obstacles. It cannot handle suddenly changing environment. It cannot handle dynamic obstacles. The good thing is it's optimal. The second algorithm is what's called as a reactive algorithm. So you just react to it. Like vivas are more reactive. If I have a viva to take at 10, by 9:59, I wouldn't have any idea what's the first question. And suddenly, whatever comes to my mind, I'll react to it. Whatever the student answers, I'll just ask a question from there. That's more reactive. It can handle dynamic obstacles. Like with different students, it can adapt. With the student not knowing anything, it can adapt. With changing maps, it can adapt. With rapidly changing environments, it can adapt. Somebody comes to hit me, I can adapt. It's continuously adapting. Computationally, it's a very cheap. So, I mean, how much time does it need to calculate the free body diagram forces and just act on it? Absolutely nothing. So it's extremely fast. And because it's extremely fast, it can handle anything. And that's what we say is the trade-off between a deliberative planning and a reactive planning. This is the me being the Vishwanathan Anand, being the planning guy, being the guy who thinks a lot, but then I cannot adapt to changes. Like I couldn't adapt to changes of the coronavirus. I'm a smart person. This is reactive planning. You just look at something and you react to it. That's a potential field. You just react. So, of course, what we do is a happy marriage between them. And the happy marriage between the two of them is based on a principle that sometimes the goal in life is too far off. Like, I have no idea what is my goal in life. I want to become a billionaire. That's too far off. So, whenever your goal is too far off, you break down your goal into sub goals. The sub goal is in the path of your main goal, and it's something that you can view. And because it's something that you can view, there's a fire in you that keeps driving you to it. It's always attainable because you can look at it. And not only is it always attainable because you can look at it, you will never divert. It's right at sight. The main goal, you have absolutely no idea. So in Fusion, that's what we do. This is what your parents do for you. So, I mean, the moment you are born, they have a plan for you. This is the PRM or the RRT. So you'll do 10th, you'll do 12th, you'll do engineering, you'll marry, you'll have a job, you'll have kids, you'll support your parents in old life, then they don't care. So your parents only have a plan for you done by the deliberative algorithm. They only show you a sub goal. Class 12, get very good marks. After that, life is settled. So this is a potential field. It uses this sub goal as the only goal in life. It's the last point visible, so there's always a straight line possible to that connect to it. And when you are moving, football matches come, US presidential elections come, something lovable in life comes, all the dynamic obstacles come, the goons outside my office, my research scholars moving, my faculty colleague moving, all these dynamic obstacles come, you just avoid them on the way such that you always have a goal visible. And because you always have a goal visible, there's always one plan to reach the sub goal, which is waiting for all the dynamic things to clear, and when they clear, you keep on moving. So at least one path is possible as long as the other people cooperate. So I get my deliberative trajectory, I break it down into sub goals. My sub goal at any point of time is the last point visible, excluding the dynamic obstacles. I keep on moving around, ensuring I always can see the sub goal. Once I'm near the sub goal changes to the last point visible. So as soon as you are about to cheer, 12th, I am about to get very good marks. The board examination is 1 week. The parents start saying engineering. So the sub-goal always adapts to the last point visible. And as you go along, the sub-goal moves along. Finally, the sub-goal and the goal are the same thing. The potential field works. So in short, the mantra is that take a deliberative trajectory shown as blue, take the last visible point as sub-goal shown as dark gray, run a potential field only on the sub-goal, which is always on this trajectory. And the moment the robot reaches a point, update the sub-goal to the last point visible. The light gray is the things which are visible, not visible. The white is things which are visible. Blue is the trajectory. The sub goal is the Sangam of this Ganga, Yamuna, Saraswati. It's the intersection point. That's the last point which is visible. That's what you see. So the robot keeps on moving. It comes here. That's the last point visible. It comes here. That's the last point visible. It comes here. That's the last point visible. So as it moves along, different points are visible, and that's what become your sub goal. So I'll end up with maybe some interesting videos. That will be the last point that I have. The first one is, now you see that it's a cheap robot, and the cheap robot does not have the expertise to make a map. So we use the bigger robot that I showed to you. This one local just by using sensors to even detect and track corners. It did not know about this toolbox, and So it's following the deliberative trajectory, saying, I know where am I know what the map is, and there are ultrasonic sensors over here. And now the ultrasonic sensors say, okay, you have a new obstacle. So it uses potential field to get around it. And now, of course, once it got around it, it just continues with the potential field algorithm and reaches out to the goal. And this is my last video. I might have also overspoken. So that's a bigger robot. So this one exactly is the home position that I showed you. And this is what I was saying. So I am here. The robot initially tried to go in a straight line here. And of course, this is the wall which has a trap. So we use deliberative trajectory to let it come around, and once it comes around, then it actually goes into the goal around over here. There's a little problem over here because there's a ditch and the robot detects it, and for safety reason it denies to go around. This one is work on an interesting project, which is basically a kind of a traveling salesman problem for robotics. So the robot had to do 20 different things. They had all the things around that you need to sequence it up, and the robot is sequencing. The audio is not visible. It's also pronouncing things up and as it moves around. So that's a one. It's not doing what is mentioned on the text because the sponsor did not allow us to get a manipulator. Neither did we have IoT devices around over here, which hopefully we'll get one day. That's a standard cheat video that everybody uses. So if you just want to do quick autonomous robotics planning and stuff like that, the overhead camera, it detects all this thing up. It rectifies the image to something which is more orthographic if you want. Otherwise, this is the map, raw image of a camera. The green color is the most distinctive, which is the location of the robot. So you track this green center of mass, and then a derivative of it is where the robot is looking at. So that's what I recommend as a naive thing for everybody to do if you just want to have a hands-on motion planning. And finally, most of the libraries, of course, are Linux, and they work great on Linux. So for Linux, still Open Motion Planning Library is the best. If you're more of a Windows guy, this is probably the best bet for you, which is the VREP as a simulator. It internally is using RRT Connect as a planner. It's got a lot of tutorials and stuff like that. You can just drag and drop robots, create environments. Again, so for elementary publication, all you could do is to look at all the scenarios that it has, simulating, take a nice application level paper, social robotics, and something like that, and just create a simulation of it, be it factory line simulation, be it simulation of robots in warehouses, be it simulation of robots in homes. So just drag and drop, simulate that up, create interesting application. It uses Lua, which is extremely easy programming language, lots of tutorials, lots of examples. You could simulate and get in early publications. And then, of course, if you want to go more, most of it has excellent interfaces with open source libraries, so you can actually program those libraries and show the improvement on a VREP. So for starters, it's one of the best simulators that I do recommend, and I hope I have a thank you slide. Yes, so that will be all for the presentation. Thank you.
Thank you so much, Dr. Rahul, for such a nice talk. Thank you so much. I hope the participants might have learned a lot from your lecture. So I think they will be motivated to do some good research work in this emerging area of robotics. Thank you so much, sir, for giving us your valuable time.
Thanks, sir.
Lecture. Any questions, please? Any questions from participants? You can ask. Participants, if you have any questions, you can ask. We have one or two announcements. So at 3:30, you all are requested to join the session. First quiz, then we have a valedictory session, and then we will take photograph of all the participants for the sending it to AICT, and then a final feedback form you all have to submit it. So we will give quiz link on your WhatsApp group as well as on your email. So you have to finish it within 30 minutes. Any question, please? Thank you, sir. No question.
So much.
Thank
Okay,
you, sir.
bye.